Welcome to ScienceCover.com. In this session, we're going to look at electric current, and we'll focus on what we mean when we talk about current, how we can measure an electric current, and how it behaves in series and parallel circuits. Now pause the video and try the Do Now task. Let's check our answers. Number 1, we had to show how we'd connect a voltmeter to the bulb. So voltmeters are always connected in parallel. So we have to connect the voltmeter to each side of the bulb. If 5 volts is supplied from the cell, what's lost on the bulb? Well, we lose what we put in. So if we're putting in 5 volts, we've got to lose the 5 volts. An identical bulb is attached in series to the circuit. What will the new voltage be on the original bulb? Well, we lose what we put in. So if we're putting in 5 volts, we have to lose 5 volts. But now we've got 2 bulbs, so we're going to lose 2.5 volts on each one. How will adding the new bulb affect the brightness of the original? Well, the brightness will go down, so it'll become dimmer. The new bulb was removed and a second identical cell was added. What will the new voltage be on the bulb? Well, if the first cell was supplying 5 volts and we've added an identical cell, then it will be supplying 10 volts. Let's start this session by looking at what we mean when we talk about an electric current. A current is a flow of charge. This could be positive or negative charge. As long as the charges are moving, then we have a current. But in electrical circuits, we usually see electrons moving from negative to positive, and so electrons are negatively charged particles. Now, to get the electrons to move, we have to create a potential difference or a charge difference. So in this diagram, we've got 2 plates, one with a 10 coulomb charge and one with a 0 coulomb charge. So we have a potential difference because the 10 coulomb charge is more positive than the 0 coulomb charge. So if electrons are negatively charged particles, they're going to be more attracted to the 10 coulomb plate. So if I connect a wire between these plates, it means my electrons are going to be pulled from the 0 plate to the 10 coulomb plate, because the 10 coulomb plate is positive, but the electrons are negative. And so we've created an electron flow. So this is an electric current. However, the cells and the work being done on electric current happened at the end of the 19th century, and the electrons weren't discovered until the early 20th century. So what it means is that we were making our rules about electricity before we actually understood about electrons and the atom. And so they had to take a guess about which direction they thought the electrons would flow in, or they thought that the particles would flow in. And so it was assumed that electricity actually flowed from positive to negative. And so when we draw current in a circuit, we actually draw the arrows going from positive to negative, and we label this the electric current. In reality, we know that the electrons move the other way. So we know now that potential difference causes current, but also that current flows from positive to negative. So if I have a cell, I have one side of the cell that's positively charged and one side of the cell that's negatively charged. And we represent these with a long line and a short line. Now, if I connect both sides of the cell with a wire, then I can show the current movement by drawing arrows to show the current flows around positive to negative. Now, a higher potential difference just means that I have a larger charge difference between my positive and negative plate. And if I do that, I should see a higher current flow. Now pause the video and attempt task 1. Let's check our answers to task 1. Question 1a was asking us to label the direction of electron flow. So electrons we know flow negative to positive, so that's shown by the blue arrow labeled E on my diagram. 1b was to use a different color and draw the electric current, so that is flow in the opposite direction from positive to negative, and you can see that on my diagram as a red arrow labeled I. Question 2, why does the conventional current travel positive to negative whereas electrons travel negative to positive? We discovered current before the electron, so the assumption was made that current flowed from positive to negative, and the conventional current has never been changed because it would require rewriting many of the electrical rules that we have. Question 3, if the cell in the diagram is switched to a higher voltage cell, what will happen to the current? Well, it should increase. Next, let's look at how we measure an electric current. Electric current is measured using a device called an ammeter. And you can see a picture of an analog ammeter on the left-hand side of this slide. But if I want to show how to connect it in the circuit diagram, I need to draw the circuit symbol, and that will be a circle with a capital A inside of it. Now the unit for current is ampere, or amps for short, and I can represent this by writing a capital A. So if I wanted to take a measurement, I could write 5A, which means 5 amps. So to take a reading with an ammeter, the current has to pass through the ammeter. So to connect the ammeter to a series circuit, I can just place the ammeter anywhere within the loop. So the current will now flow through the ammeter, and it'll tell me how much current is traveling around my circuit. But in a parallel circuit, we have different branches, and so I can measure the current at different locations. If I want to measure the current going through the cell, I need to place an ammeter on the branch that the cell is attached to. If I want to measure the current passing through the first bulb, I need to place an ammeter on the branch that the first bulb is attached to. If I want to measure current traveling through the bulb on the second branch, I need to place an ammeter on the second branch. Now, it doesn't matter whether I put the ammeter before or after the bulb, the current will still flow through the ammeter. If I want to measure the current on the third and final branch, I need to place an ammeter on the third branch. Pause the video and attempt task 2. Let's check our answers to task 2. What is the name of the device used to measure electric current? It's an ammeter. Sketch the circuit symbol for an ammeter. It's a capital A within a circle. Add an ammeter to the circuit to show how we could find the current around the circuit. Well, you can place the ammeter anywhere in the loop. So I've placed it after the bulb, but you're equally correct if you place it before the bulb. Add an ammeter to this circuit to show how we could find the current of bulb A. Well, your ammeter has to be on the same branch as bulb A. And question 5, add an ammeter to show how we can find the current of bulb B. Well, your ammeter needs to be on the same branch as bulb B. Now let's focus on series circuits. This is a series circuit as it's got one loop. We've got a bulb and we have a cell. So let's place 4 ammeters in our circuit. One as the current leaves the cell, one as it enters the bulb, one as it leaves the bulb, and one as it re-enters the cell. So the cell is going to produce a potential difference, which is going to create a voltage and start our current flowing. Let's say we have 2 amps of current passing through the first ammeter. Well, those electrons are going to carry on moving down the wire and pass through the second ammeter as well. So we would expect them to have the same current, 2 amps, and then the current enters the bulb. Now, the current is how many electrons are flowing, and what causes the bulb to light up is actually the energy that they're carrying, which is the voltage. So the electrons themselves are not used up by the bulb, which means that they're going to pass out the other side of the bulb as well. So we're still going to have a 2 amp current entering the bulb and leaving the bulb because the electrons are not used up. And so this 2 amps is going to carry on traveling through the wire. It's going to reach our 4th ammeter, still 2 amp current, and then it will return to the cell. So all through this series circuit, we have the same current, which in this case is 2 amps. Let's look at an example. We have a 5 amp cell and a bulb connected in series. So if we place a couple of ammeters in the circuit, between the 5 amp cell and the first ammeter, there is no components, so the 5 amps must pass through the first ammeter. When it passes through the bulb, we know that current doesn't get used up, so 5 amps must come out to the bulb, so 5 amps will also pass through our second ammeter. So in the series circuit, we have the same current all around. Now pause the video and attempt task 3. Let's check our answers to task 3. In a series circuit, current is the same through all the circuit. This is because current does not get used up in components like bulbs, so we see the same current into and out of the bulb. Voltage gets picked up at a cell by electrons and will be lost at the components like bulbs. So the missing words were series, same, used, current, voltage, lost. If A1 reads 5 amps, what will the current be at A2? 5 amps. Now let's look at how current works in a parallel circuit. This parallel circuit has got one cell and then 3 bulbs in parallel. So we could place an ammeter on each branch to measure the current at each location. So let's say we measure the current coming from the cell as 12 amps. Well, when it gets to the first junction, some of the current will pass through the first branch, but some of the current needs to go to the second branch and down to the third branch. So the current will actually split up. And what we'll see is that only 4 amps will pass through the first branch. Now the other 8 amps passes down to the second and third branch, and again it splits up. So we'll have 4 amps going through the second branch and 4 amps going through the third branch. So of our 12 amps, a third of the current went through the first branch, a third of the current went through the second branch, and a third of the current has gone through the third branch. And that splits our 12 amps equally, 4 amps, 4 amps, 4 amps. So you've just seen that when the bulbs are identical, the current splits evenly, but what happens when they're not identical? In this situation, we have a 12 amps coming from the cell, and it will split between a 1 ohm bulb, a 2 ohm bulb, and a 1 ohm bulb. Now, I've got my 3 ammeters, one on each branch to measure the current, and the current split will be 4.8 amps on the first branch, 2.4 amps on the second branch, and 4.8 amps on the third branch. Now we can see there's a relationship between the resistance of the bulb and the current that's taken that route. So for instance, if we look at the central branch, the 2 ohm bulb has got twice as much resistance as both the other bulbs in this circuit. What that means is only half the amount of current chose to take that route. Now pause the video and try task 4. Let's check our answers to task 4. The missing values for A2 and A4 in the first row were 4 and 4. In the second row, A3 was 5 and A4 was 5. In the third row, A1 was 9, A2 was 3 and A4 was 3. And in the final row, A1 was 18, A2 was 6 and A3 was 6. In question 2, the bulbs are swapped for 3 different resistances as shown. Complete the table to show the currents at each ammeter. Well, A3 in the first row was 8. In the second row, A4 was 3. In the third row, A1 should have been 20. And in the fourth row, A2 was 6, A3 was 12, and A4 was 6.